In this video, I want to talk about the CMOS inverter timing and layout. By timing, I mean how fast the inverter can respond. If I give the inverter an input, how fast can the output of that inverter discharge a capacitance? Now let's start by reviewing the MOSFET transistor. Here I have an N-channel MOSFET where the orange is an N-type silicon and the green is a gate electrode. Now let's suppose that I want to ground the source region of my MOSFET, and to the drain I want to attach a capacitor with the bottom plate at ground, and let's say that this capacitor is charged up, and I want to raise the gate voltage, turn on this MOSFET transistor and discharge the capacitance, and I want to do that very quickly. So let's review the MOSFET operation just very briefly. Now when I raise the gate voltage relative to the source voltage, I form a channel region in this MOSFET transistor, and that causes current to flow from the drain to the source. Now the key thing I want to point out is that as I make this transistor wider, as I increase the width, I increase the region of the current flow from the drain to the source. And I can think of this channel region under the gate as a resistive material. So let's think of that as a channel as having an equivalent resistance that connects over to my capacitor with the bottom plate at ground. So when I raise the gate voltage, I cause this channel resistance to form. I'll call it R. And I want to discharge this capacitor C that is charged up. And basically the source is connected to ground. So recall that if I multiply R times C, I get time. So if I can make the R very small, I can make the time very fast. The R times C gets smaller. So the key thing is that the wider I can make the width of the transistor W, the wider W, the more region I have for this current flow, and the smaller the resistance. So as I make the transistor wider, you can think of this as adding resistors in parallel. And as we know from previous videos, resistors in parallel decrease the overall resistance. So the resistance gets smaller and the time gets faster. Now the other thing I can do to improve the time or to make it very fast is to reduce the channel length. And let me erase a little bit here. But let's think of what happens if we, instead of reducing the channel length, if we increase the channel length. If we increase the channel length, we add resistance in series with the current flow. So I'm adding resistors this way. And resistors in series increases the total resistance. And increasing the total resistance slows things down. So if I want this transistor to operate fast and discharge this capacitor very rapidly, I want to make W very wide, and I want to make L as small as I can. So let's now review the schematic for the CMOS inverter. Here I'm in my schematic capture program, and notice that I've captured 3 different inverters. The first one is here, the second one is here, and the third one is over here. And notice that the output of each inverter is connected to a 1 picofarad capacitor. this voltage source here generates a 2 volts power supply that feeds across here to our P-channel transistors. And notice that the source of each N-channel transistor is connected to ground. And also notice that all of the inputs of the inverters are connected together over to this V2 voltage pulse. Now this V2 voltage pulse generates a quick little pulse that starts at time 0, it starts at 0 volts. 1 nanosecond later, it switches up to 2 volts, stays at 2 volts for 10 nanoseconds, and at 11 nanoseconds, it comes back down to the ground level. Now notice that my channel width and my channel length for both transistors are 1 micron for the first inverter. So it's going to be a slow case because it's not a very wide channel and it's a longer channel length. Now notice that the second inverter has the same channel length of 1 micron, but the width is 5 microns wider. So it can produce a greater current that's going to discharge and charge this 1 picofarad output capacitance. Now notice my third inverter has a wide channel length at 5 microns, but the channel length has been reduced from 1 micron to 0.2 microns. So this should be the fastest case. So let's do a simulation. I'm going to select my run icon. And let's probe some of the circuit nodes. Let's look at our input node. And you see the input pulse switching up to a logic 1, staying at a logic 1 for about 10 nanoseconds, and then switching back to a logic 0 level. So let's probe our supply voltage and make sure it's at 2 volts. And that's shown here at blue, and that looks good. Now let's probe our slow inverter case and look at the output. So here we see that in red. We see that the output starts to discharge the capacitor, but never really does a very good job. It never gets to a logic 0. So it's just really much too slow. Let's look at the output of our second inverter. And we see that the wider transistor, by increasing the width by a factor of 5, it discharges faster, but never really gets to a logic 0. So let's look at our third inverter output, where we have reduced the channel length from 1 micron to 0.2 microns, and it's still at the wide width of 5 microns. So here we see a very decent inverter response. So we have the input rising up and the output being inverted to a logic 0 and becoming a very solid logic 0 at this time. When my input goes from a 1 to a 0, the output goes from a 0 to a very solid 1 at this point. So hopefully this gives you the idea, let me get rid of this, that a very wide channel width gives a better drive. It produces more current to discharge and charge the capacitor, and a very narrow channel length provides more drive current and makes the inverter faster. Now I'm in my layout editor. So let's lay out a CMOS inverter. And I'm going to do this with my automated layout tool. So I'm going to call that up, default. And now I'm going to list my devices. Let's select INV for inverter. And it wants a name. So I'll give it a name. It's asking for my channel length. I'm going to make it 0.2 microns for both the NMOS and the PMOS. Let's set the P channel width at 4 microns and the N channel length or the width at 2 microns. And this is the layout that's produced. Now I want to go into my tool and generate another cell that will connect to the N well that houses the PMOS transistor and connect to my substrate. This easy default.lv list. Let's select tie, T-I-E. Give it a cell name. So this provides connections to my well and my substrate. So this region here is a region of my P-channel transistor. This region here is a region of my N-channel transistor. This region here connects to the surface of the wafer or to the substrate. This is a P-type diffusion because my wafer is P-type. Now this magenta region is the N-well region. This is an N-type region that houses the P-channel transistor. Now this region here provides a connection to this N-well and connects it up to my power supply. This is my high voltage power supply up here, and this is my low voltage power supply. And we'll explain this in more detail. Let's turn off some of the layers and look at each masking layer for this inverter. So let's blank layers and well invert return. So now I'm just showing my N-well layer. Let me change the fill code to let me get rid of this. Pattern, make it a solid pattern. So this region is going to receive an N-type diffusion or implant, and everything outside of this region is P-type silicon wafer. So this is the surface of my wafer. So I'm going to change the fill pattern back to just an outline. Now let's take a look at the active layer mask. Let's do unblank layers, active return. So this shows where my P-channel transistor is going to exist. This diffusion is going to make a connection to the N-well. This diffusion is going to be the location of my NMOS or my N-channel transistor. This is going to provide a connection to the substrate. Now this diffusion or blue region, I want to be P-type. This blue region has to be N-type. This blue region should be N-type, and this should be P-type. So there are two layers that determine whether it's an N-type or a P-type active. So let's turn those layers on. Let's do unblank layers and implant return. So this layer will guarantee that this active is an N-type, this active is an N-type. So let's unblank layer P implant return. So this yellow layer will guarantee that this blue region is a P-type material, and this blue region here is a P-type material to contact the surface of the wafer, or what we call the substrate. Now, I need to have a gate layer or a polysilicon layer, so let's unblank that masking layer. Now that's shown in green. So this region here, this green, is the gate electrode for my PMOS transistor. This green, where it overlaps the blue, forms the NMOS or the N-channel transistor. Now recall that the gate acts like a shield. So when the diffusion is implanted into this drain source region, the actual diffusion ends up in the blue region that is outside of the green region. It ends up in here. And the same for the NMOS transistor. The source and drain active diffusion regions end up in the blue region here that is outside of the green region. So it's in this region, but not in this region. Now where the green layer overlaps the blue layer is a channel region. So this is a channel region of my P-channel transistor. This is a channel region of my N-channel transistor. Now we need to have contacts to these different regions of the transistor. So I'm going to unblank layer, the contact layer. And let me also, I'm going to add a little cell here. It's going to make contact to this green gate electrode region. And that has two white contact regions. So these white squares are going to connect these silicon layers to a layer of metal that sits above. So let's unblank the metal masking layer. And the metal layer is shown in red. And so all the contacts connect the silicon below to the metal above. Now in this process I have another layer of metal, and that is called second metal, and it connects to this red metal one by another masking layer that's called a via. So the via provides the connection between the metal 1 and the metal 2. So let's unblank layers at VO1 return. So you can see that there's via layer here, some here, there's some vias here, some vias here. So they're going to connect to the second metal. So let's unblank layer metal 2 return. So the second metal is shown in yellow. And let me just do view MET. So let me turn off the silicon layers. And now we see just the metal layers. So this metal layer here forms the output of the inverter. This little metal layer in red is connected to the inverter input. This metal connects to my PMOS transistor source. This metal layer connects to my NMOS transistor source. This metal connects to the wafer surface or the substrate. This metal connects to the N well that houses the PMOS transistor. So let's turn off the metal layers and view just the silicon layers. And view all. So I'm going to just zoom in here. S view. There we go. So this is my NMOS region. These are contacts to the polysilicon gate material. This is my PMOS transistor. This is the gate of the PMOS. And this is my power metal shown in yellow. So let's do view all. So hopefully this gives you some idea of the different masking layers needed for the CMOS inverter. I'll call it R, and I want to discharge this capacitor C that is charged up. And basically the source is connected to ground. So recall that if I multiply R times C, I get time. So if I can make the R very small, I can make the time very fast. The R times C gets smaller. MOSFET transistor and discharge the capacitance. And I want to do that very quickly. So let's review the MOSFET operation just very briefly. Now when I raise the gate voltage relative to the source voltage, I form a channel region in this MOSFET transistor. And that causes current to flow from the drain to the source. Now the key thing I want to point out is that as I make this transistor wider, in this video I want to talk about the CMOS inverter timing and layout. By timing, I mean how fast the inverter can respond. If I give the inverter an input, how fast can the output of that inverter discharge a capacitance? Now let's start by reviewing the MOSFET transistor. Here I have an N-channel MOSFET where the orange is an N-type silicon. As I increase the width, I increase the region of the current flow from the drain to the source. And I can think of this channel region under the gate as a resistive material. So let's think of that as a channel as having an equivalent resistance that connects over to my capacitor with the bottom plate at ground. So when I raise the gate voltage, I cause this channel resistance to form, and the green is the gate electrode. Now let's suppose that I want to ground the source region of my MOSFET, and to the drain I want to attach a capacitor with the bottom plate at ground, and let's say that this capacitor is charged up, and I want to raise the gate voltage, turn on this